Okay, so I'm proud and happy to present Professor Yakir from the Weizmann Institute, a plant ecophysiologist, the 2019 Israel, the winner of the prestigious Israel Prize for Research, also for his groundbreaking insights into the impact of semi-arid forest on the global climate. Dan has through the years many students and will present his groundbreaking work, and I'm happy to have him here. Professor Dan Yakir, please, the floor is yours.
Okay, thank you, Shimon. Let me do the sharing. Okay, so hi everybody. I cannot see anyone. I don't know who is behind the screen, but I hope there are a few people, and thank you for joining this lecture. And I will tell you why forests at the dry timberland are important to probe the ecosystem scale response to change. So in these strange times of COVID-19 pandemic, I thought to start with a few words on this, on the impact of the pandemic on the environment. And this is actually quite a complex picture because we do see a significant impact. We see these amazing pictures of famous sites around the world, like the Taj Mahal on the top left-hand side. It's very unusual visibility. We see pictures like on the top right-hand side also from India, where you see the visibility before the closure and during the closure, a very strong impact. And also, increasing number of papers actually come up with actual numbers and data, like the pictures I showed below. And this is for nitrous oxide, one of the pollutants that are very important in the atmosphere. But in fact, there are many other nitrous oxide particles like PM 2.5, carbon monoxide, and sulfur dioxide. But in the pictures, we see two examples, one from Italy, especially from northern Italy, where there was a major problem, major impact of the pandemic. You see the nitrous oxide concentration below the closure and immediately following the closure on the right-hand side, a very dramatic effect. On the right-hand side, we see another example from China, where everything has started. And again, you see the left picture, nitrogen oxide in the atmosphere in January, then in February, and then at the height of the closure in March, a pretty dramatic decrease in the pollution. But when we look at CO2 and other greenhouse gases, the picture is more complicated. Of course, the slowdown in the activity was reflected in a decrease in emission, and this is a significant number. The numbers here on the scale are in millions of tons of carbon dioxide. And we see the start of the pandemic effect in China, a major decrease in emission, and then quickly spreading to the rest of the world, again with impressive numbers. But if we look a little bit closely at the number, and we can use, for example, the table on the right-hand side, we see that the major effect were in the transport and aviation, so 23% reduction in the aviation and more than 15% decrease in transportation. But those are actually a small fraction of the global emission, and when we weight it by the total emission of all sectors, it translates to less than or about 3%. And combined, everything else is translate to just above 7% reduction in total emission of carbon dioxide. Not a huge one, and not as dramatic as we see for air pollution. And indeed, when we look at the CO2 increase in the atmosphere, we still see this relentless increase in CO2. And we see the seasonal wiggles that are due to the biological activity that we're going to discuss further later. And if we zoom in to the last seasonal cycle, we see that this just above 7% decline in CO2 emission translate to a small decrease in the minimum, the summer minimum in the seasonal cycle, which is estimated to be at around half a ppm. So the concentration continued to increase, and now it's well above 410 ppm. And the reduction due to this massive decrease in activity is barely at the detection limit of our measurement of atmospheric CO2. And of course, we cannot expect that such a small decrease in greenhouse gases will influence temperature. And indeed, September, just a couple of months ago, was the hottest September on record. And you can see that its temperature is about 1 degree Celsius above the average based on the NOAA data. So the COVID-19 pandemic clearly had a major impact, of course, on us human beings, on pollution, on health, but in terms of global warming and climate change, the impact is smaller, and it shows the challenge for us in reducing total emission. And this reminds us that there are other players in the system, and we have to remember that the land biosphere is an important player. So here's an example of the global carbon budget. Today we emit about 10 billion tons of 10 gigatons of carbon every year, mostly from industrial activity and also from land use change and deforestation. But less than half of it actually remain in the atmosphere, and the other half is reabsorbed by the ocean, dissolution in ocean water, and through photosynthesis in the land biosphere. And the land biosphere, which is our interest, today absorb nearly 30% of our emission on an annual basis. So a major player in the system, and we have to remember this factor. And not only that it's important player, also it increases its activity and its absorption as we go along. So over the last 150 years, the emission has increased, but the absorption through photosynthesis, or what we call GPP, gross primary productivity, has increased in pace. And in this example from a paper published recently, the argument is that the main reason for this increase is actually the CO2 fertilization in the atmosphere. So we increase CO2 in the atmosphere by emission, and this enhance photosynthesis, and photosynthesis continues to absorb about 30% of the emission. However, we also have to remember some caveat in this picture, and that when we look at GPP, or the uptake in photosynthesis, this is not the whole story. And on the right-hand side, you can see an example from a recent paper from a large-scale experiment in Australia, in a phase experiment where there's a carbon dioxide enrichment. And indeed, what they see is, what we see in the purple here is a significant enhancement of GPP, increase of CO2 uptake, but at the same time, also enhancement of the various respiratory processes and the loss of CO2 back to the atmosphere. We don't have time to go into the various detail, but we can go all the way to the right-hand side of the picture, and we see that this parallel enhancement of GPP on the one hand and the various respiratory pathway on the other hand result with essentially zero change in the carbon accumulation in the system in the various components here. You see in the stem, in the roots, in the soil, in the litter, and so on, and it's all around zero in the right-hand side of the figure. So this is an important factor that reminds us that when we are interested in looking at the carbon pool, we have to consider not only the fluxes in and out of the system, but also the carbon turnover time, which is a key factor in controlling the carbon pool. And I will mention this in a few slides down the road again. So CO2 is going up and the photosynthesis is going up, but this is not going to go to continue forever. In fact, there are increasing number of papers that already point out that this trend is slowing down and maybe decreasing, and the greening of the biosphere in many regions is turning into the browning of the biosphere. And part of it is that part of the reason for this is the climate is changing in parallel, and this is just one example that is relevant to our conference here on desertification. And this is essentially the global scale increase in aridity index. As the climate is warming, there is an increase in precipitation. Of course, the ocean is warming. Ocean is warming is enhancing evaporation and enhancing precipitation. But the transfer of moisture from the ocean to land is not linear, and it's not in pace with the warming of the ocean. And the increase in precipitation over land is relatively slow. And as a result, the land area is drying, and the potential evapotranspiration is increasing faster than the increase in precipitation. The potential evapotranspiration is defined at the bottom of the slides, but it is essentially the evaporative demand or the dryness of the atmosphere that is sucking the moisture from the land and from the vegetation. So the ratio of the P over PET is intensifying, essentially increasing the aridity, as defined by the UN today, the ratio of P over PET. And of course, we are concerned, especially in conferences like this, to what extent land areas are moving through these different categories of drylands, from temperate to subhumid, from subhumid to semi-arid to arid, and so on. And we know that there are significant land areas that are moving up this scale, and this, of course, also influenced the activity of the biosphere. This is just to highlight that this increase in potential evapotranspiration is especially due to the increase in VPD, vapor pressure deficit, that we know that should increase in the atmosphere, and as the model showed, the blue line in the background, and it's already increasing and expected to continue to increase, and the data, the color points are consistent with these expectations. And in this particular paper, they already show that this increase in VPD has an effect on the vegetation activity, and it reduces vegetation growth. So on the one hand, we have the CO2 fertilization effect that is greening the biosphere, enhancing GPP. On the other hand, some other factors are acting against this trend. So if we stop for a moment to summarize the introduction, we saw that COVID-19 demonstrated the challenges we have in emission reduction. In fact, it is estimated that we need the same impressive reduction in activity that we saw this year, every year for a decade at least, to make the Paris Agreement. So certainly it was a humbling demonstration of the challenge involved. On the other hand, we're also reminded that the land biosphere is an important player, and at the moment, even more important player than our attempt in reduced emission. However, aridity index is enhanced globally, the ratio of precipitation to potential evapotranspiration. There is contrasting effect of the fertilizer effect of CO2 enrichment increasing on the one hand, and the VPD effect, stomata closure, and decreasing growth on the other hand. So productivity is so far increasing, but there are signs that this is not going to stay with us forever. And therefore, we have to search for indications that the plant can adjust to the trend, the changes in the climate, they can resist it, or any other way that they can stay an important player in the system. And we think that a major effort should focus on the hot and dry timberline, because this is the direction in which many of the land areas and ecosystem are going this way. And in more simple ways, we want to see the potential of the plants to sort of fight back the system, and this is what I'm going to show you in the next few slides from our research side. So for this, we need to zoom into from this hand waving and global scale perspective, and go down to the ecosystem scale, and even to the single tree and the organism processes. And this is a very dramatic movie from NASA that show one important forest, but in fact, my argument today is this is the wrong forest to go for the purposes that we just described. We have to go to a different forest, and this is our forest, the Yakir forest, at the edge of the Negev Desert in Israel. This is, I think, where we can see the potential of plant to adjust and resist the increase in the aridity index that I mentioned before. So now I'll give you a few examples from this site that we have been working on for the past 20 years. Quite early on, about 10 years ago, we already noticed some major adjustment in the system. And when we compared the seasonality of GPP in various pine forest sites all the way from Finland in the north, latitude of 62, through Belgium, France, Spain, all the way to Yakir in Israel in latitude 31. We see when we look at the normalized GPP, a very strong shift in the seasonality from peak activity in July, August to peak activity in Finland, to peak activity in Yakir in Israel around March. When you look at the temperature during this peak activity, we find that this remains in a very narrow range, even though we move from a very cold, wet environment to very dry, hot environment. And this shift results with a very narrow range of temperature during the peak activity, and we call it this kind of global scale homostatic response. So this was already early on. We noticed that there are adjustment and changes in the dry system compared to other pine forests, in this case across Europe, but also in the rest of the world. In the last couple of years, we looked at much more details in this kind of response in our neighborhood, in the Eastern Mediterranean area. And here we are comparing a leopard pine forest in Greece, the sunny forest. This is a latitude 38 with Yakir, much closer compared to Finland. And this is a work of Nikos Markos that is now being prepared for publication. So here I want to highlight two aspects. One, that you still see the very strong shift in the seasonality from peak activity in the summer to the very early peak activity in the spring, around March, April, but also a shrinkage of the activity period. So in Yakir, we have a very sharp and narrow peak of activity, and in more temperate areas, the peak not only is later, but it's much wider. You can see the change from the peak activity when it's above, at the top 15% of the activity level. The period is over 120 days, and in Yakir, the period when activity is at top 15% is less than 50 days. You can see similar shifts in the water, but here you can see another important point, and that's the increase in water use efficiency, which is the ratio of carbon uptake to water loss. And you see that there's rather modest decrease in the peak rate of GPP, but there's a massive decrease in the water loss in the ET when we are going from the Greek forest to the Yakir forest. And of course, that means that the ratio of GPP to ET is increasing. That's the water efficiency. I just want to mention that the difference between sunny and the conditions in sunny and Yakir, the average temperature is 2.5 degrees hotter in Yakir, and the precipitation is about 35% lower in Yakir compared to sunny, which is not very different than the climate change scenarios that you find in the IPCC. So in fact, what we have here is a sort of a space for time experiment where we show for the same species how it can adjust to quite a dramatic change in environmental conditions. We also try to understand how the system is adjusting and managing with this very narrow early peak of activity. And a paper that just came out in ERL of our PhD student, Wang Wang, And some of the highlights of this study is summarized in these slides. What we see is this early peak of activity around March and April. And you see that this peak sits in a sort of a sweet point between the very sharp decrease in soil moisture into the hot and dry summer, and the increase in environmental conditions such as air temperature, which is too cold in the winter, and it has to warm up to support this peak of activity, and solar radiation, which is low in the winter, and it's peaking only later in the summer. So the peak activity sits in this very narrow combination of remaining moisture but increasing, improving conditions themselves for radiation and temperature. And it turns out that this is not the only support for this narrow peak. There is actually a remobilization of a range of factors that are summarized here. So the blue line represents near-infrared reflectance that indicates some structural changes like leaf orientation that enhance absorption of solar light in this early season. It shows that the light absorption coefficient of the leaf is enhanced at this time, and it's interesting that the peak enhancement is in the early part of the active season when the light is low and you really have to push the activity up, and it's exactly the time when this light absorption coefficient is peaking, and then more or less in line with the peak activity, leaf chlorophyll is optimized and the light use efficiency is maximized. And these are the patterns that are very different from what we see in many temperate forests. So there is what we call here, I highlighted here, a range of processes that intricately converge to support the early spring activity, and we call it the Goldilocks effect, because it's really, if you remember the Goldilocks story, we really have to optimize a lot of parameters all at the same time across a very narrow window to support this observation. Now, I also mentioned that after this very narrow window of activity, there's a very long, hot and dry and stressful conditions. And the trick of the system, or any system that has to deal with this kind of climate, is not only to support the peak activity in the spring, but also to protect itself during the long, stressful summer. And this is work by Kadmi and Saik and other people in our group that was published recently in Tree Physiology that summarize the leaf scale light energy allocation that show the photoprotection processes the forest develop for this period. And you can see here a comparison in this energy allocation in percentage of the total incident light for the optimal conditions where everything is hunky-dory to the stressful conditions in the summer. And you can see that the protection mechanism work all across the system. Initially, there is a measurable reduction in fact, a measurable increase in the reflectance of the leaf, so they avoid excess radiation absorption. The absorption is consequently reduced under stress, and of the energy that is actually absorbed by the leaf, a lot of it is dissipated as heat, again to protect the photosynthetic mechanism, and you see this massive increase in thermal dissipation, xanthophyll cycles, crotonids, and other similar processes. And eventually, only a small fraction is going into photochemistry when the system actually cannot handle more than a small fraction of the energy. CO2 simulation continues throughout the summer, throughout the stress period, but in a very low level. And if you look at this number, you can see that the proportional contribution of photorespiration is actually increasing, serving as a last resort of protection on the photosynthetic system. So we have a combination of both developing all the means to support a very narrow, strong peak of GPP activity, and then a suite of adjustment and protection mechanism to survive the long and dry summer. Now, we don't only want to protect the GPP and stay alive, we actually want to store carbon, as we mentioned in the beginning. And for this, I already highlighted the fact that the carbon turnover time is very important. And this is also highlighted in the results of one of the papers of Rafat Kubacha in our group that was published last year, where he showed that in a dry forest like Yakir, most of the carbon is accumulated below ground, over 71%. And the turnover time is slowing down dramatically. And when you compare the turnover time in this forest, you can see that it's much longer than in tropical, temperate, or boreal forest elsewhere. If you look at the total ecosystem, the effect is much reduced because the small proportion of carbon above ground has a much higher turnover time. But again, most of the carbon is below ground, and it maintains very high turnover rate. So the potential to store carbon, even though this is based on a narrow active period and lower GPP, is high and compensated by these kind of effects. We always look at both the carbon and the water aspects, and this is just another example to show a key adjustment that we see in Yakir and probably exists in other places, but it's more pronounced in ecosystems like Yakir, and this is the comparison of the subflux, the water that goes from the soil through the plant, and the transpiration, the water that we measure at the leaf scale or at the branch scale going up out to the atmosphere. And on the right-hand side, you see what happened in the wet season, when the tree is acting as a pipeline from the soil to the atmosphere, and there is a coordination between the subflow in red and the transpiration in the blue. And the timing is the same, it reaches a peak activity around noon. This is part of a much larger work of Yakir Preisler. Some of it is already published and some of it is just about to be published. But the point to highlight here is what happened in the summer when there's not much soil water and the trees still try to keep some activity. Then there is a very strong shift in the transpiration to early morning, peaking around 7 o'clock in the morning when the conditions are still reasonable, VPD is not very high, and so on. But the subflow, it does not make this adjustment, created a very large delay of up to 5 hours between the supply of water into the trees and the transpiration from the leaf to the atmosphere. And this is a key adjustment because only by doing the transpiration early in the morning, the water potential of the trees can remain below the threshold of 2.8 megapascal, which is the P99, or the the threshold for failure of the hydraulic system in the tree. But this is also a major support for the transpiration from water storage in the trees that can account for up to 45% of this peak of transpiration in the morning. So somehow, even though we cannot yet identify all the detail of this water storage, we know that there is a water storage that is filled up by subflow and providing a big fraction of the transpiration early in the morning, protecting the trees from hydraulic failure. Speaking about water loss, we see another dramatic adjustment going back to the comparison between the sunny forest in Greece and the Yakir forest. And this is the effect of VPD on the water loss. So in sunny, when it's not water limited, we see almost a linear response of evapotranspiration to VPD, increasing quite dramatically all across the range that you can observe in sunny. When you go to a place that is water limited, the control from the demand from the VPD is disappearing, and now the control is by the low water limitation from the soil. It becomes much less sensitive to VPD, and the VPD effect is negative. It's causing stomata closure and prevent the water loss that would occur otherwise if the atmospheric pump will be free to suck water from the tree. So a very strong physiological protection and conservation of water under the dry conditions in Yakir. It is interesting that while this is what we call the space for time, using the climatic gradient between Greece and Israel and demonstrate it very nicely, we can actually reconstruct this effect in Yakir itself by providing supplement irrigation in the summer. And we do have a large-scale manipulation experiment that is running in Yakir now by our students. I mentioned Yakir Preisler, and now it's Itai Oz that is continuing this. And you can see how, again, the control trees, normal conditions there with insensitive response to VPD, and with very large range of VPD. But if we add water, we remove the limitation from the soil, then we reconstruct the response we see in sunny, essentially linear response to VPD, even to very high levels of VPD, transpiration increased dramatically. And of course, this reflects a physiological control. You see in a controlled condition, very strong depression of conductance. When you apply water, stomata open, and the atmosphere take over the control. Now, I want to highlight the point that the transpiration rate here is increasing by an order of magnitude. So if under control, the transpiration is about around 0.4 millimole per meter square per second. When we supply some soil water, it can go up to around 4 millimole per meter square per second, a factor of 10, of order of magnitude. This is interesting because if you suppress the evaporation, you actually lose one of the major control of temperature of the vegetation. We know that leaf temperature is controlled mainly by evaporation. And a priori, we could expect that this stressful condition will be problematic in terms of leaf temperature control and some potential damage, and maybe even the risk of survival of this forest. But this turns out to be not the case. And this is very dramatically demonstrated in the work of Jonathan Muller, who is doing a PhD in our group, and together with Eyal Rothenberg, developed a novel and precise system to measure leaf temperature, single needles under field conditions with appropriate calibration and correction for backgrounds and so on. And now that they have this means to measure leaf temperature, and they look at the delta T, the difference between leaf and air temperature, as a response of PAR, photosynthetic active radiation, in this manipulation experiment where the rate of evaporation is different between the control and irrigation by an order of magnitude, by a factor of 10. And surprisingly, there is actually no difference in this delta T, and in both cases, it remains below delta T of 2 degrees between leaf and air temperature. This is very surprising, and the only explanation to explain the heat dissipation, the heat loss of the leaf under these conditions is to produce a sensible heat flux. There's no evaporation, it's highly suppressed, as I showed in the previous slides, and the only alternative mechanism is to produce sensible heat flux. And since the delta T is not changing dramatically, the key to produce a large sensible heat flux is to reduce the aerodynamic or the boundary layer resistance to heat dissipation between the leaf and the atmosphere. It turns out that this is also operating not only in the leaf scale, but also on the canopy scale. And this system switching from what happened in a temperate forest when we have dense canopy and the evaporation helps to control the temperature. If we have more radiation, there's more evaporation. When you move to a dry forest, when there's no water to do this, the other changes like the canopy is much open, the roughness increase, and the aerodynamic coupling, the aerodynamic resistance between the canopy and the atmosphere decreases, which support again the generation of massive sensible heat flux. even though the temperature difference is not dramatic, but the aerodynamic resistance is decreasing dramatically. This air cooling system can result on average temperature difference between the forest and the surrounding of 5 degrees, but during the summer, this difference can be 20 degrees or larger. So very effective system, but it also can be expected to produce massive fluxes of sensible heat flux. And it seems that this massive sensible heat flux is influencing not only the temperature of the canopy, but also the atmosphere above it, the planetary boundary layer. And in a series of papers we published in recent years in collaboration with scientists in KIT in Garmisch in Germany, we actually studied this effect on the planetary boundary layer above the forest. Here you can see some measurements of a oscillometer, a type of a LiDAR or a simple LiDAR. And you can see that at night, this LiDAR helps us to identify the top of the boundary layer. And you can see that at night it's about 200 meters, but early in the morning when the sun is shining, hitting the surface, and this sensible heat flux is generated, there is an impressive increase in the boundary layer that can go above 2,000 meters, and then in the afternoon, in the evening, the system is relaxing. As I mentioned, we've studied some of the detail of this phenomena. We can see how it develops, and we can show that even in a relatively small model system like Yakir, and we have to remember this is the largest forest in Israel, but it's still a model system where we study this phenomena. But even then, the increase in the boundary layer thickness can be a few hundred meters. And of course, this is proportional to the size of the forest. So indeed, we always wanted to study the details, the physics, the ecophysiology in our model system, but we always wanted to know what would be the effect in a larger scale. And at least in one case, we did that, and this is in the framework of the PhD of Gil Yosef in our group that was published a couple of years ago using a global circulation model. Gil essentially planted in the forest, in a Yakir forest in two regions in the world that have the same precipitation as in the Yakir, the same radiation regime and so on. One in Africa in the Sahel and one in Australia. Here you can see the results from the Sahel. The black square is the area where he planted our Yakir forest, but instead of a couple of thousands of hectares, tens of millions of hectares across the Sahel. And you can see the results of the impact of the forest on precipitation and on temperature. And the colors here show the average results. You can see that there is increase in precipitation during the wet period and a decrease in the surface temperature. And he ran the simulation for 15 years, and you can see that the response was very robust. Here, the increase in precipitation, you see it mostly above the zero line, so increase in precipitation, even though there are interannual variation, El Nino, La Nina effects, and so on, the effect is very robust. And the same for temperature. You see that it's very robustly below the line, always cooling of the surface. And another interesting aspect that you see the effect is going well beyond the original area where the forest was sort of planted in the forest. So it enhances the expansion of this effort. So we can see that some of the principles then in the parameterization that we developed in a small forest like Israel influence not only what happened in the forest and the ecophysiology, but also influence the atmosphere and the environment, and also provide a basis to scale up this kind of responses to much larger scale. For example, the convector effect that I mentioned is very dramatic in Yakir, and it's hardly identified in other places, but it's not a phenomenon that is unique to the Aleppo pine in Yakir. It's just very pronounced there. It's something very important to remember. So let's go back to our summary of before with some small changes. So we started by noting that the COVID-19 demonstrated the challenges in emission reduction, and this reminded us the importance of the land biosphere, which is still an important player, and especially an important one as long as we are not up to the challenges in the global emissions. And this motivated us to search for indication of plant adjustment to climate trends, and this led us to the research in the dry timberline. And this research showed us that there are clear indications of the potential of plants and ecosystem to what I call to fight back the climatic trends. There's no question that there is a potential. Of course, the end result is not known. It depends how extreme the climate will be. Eventually, mortality is also increasing, and we cannot rely on the plants to keep adjusting and resisting all these changes. But what we know already should motivate us to protect the land biosphere in general as an important player in the system, ameliorating and slowing down the changes. And in particularly, of course, we are promoting this activity in the land area, in the dryland areas, which are vast in area and still have a potential in terms of contributing to the land biosphere activities. And as I mentioned, as I showed in the last slides, we also point out to some directions that we can take to exploit the plant activity in some sort of a geoengineering direction, and not only monitoring what is existing. We actually can somehow manipulate and influence what is going on to some extent. I think this is the end of my short demonstration of why it is important to study what happened in ecosystem in a dry timberline. But I cannot finish without pointing out that all this work over, in our case, over 20 years is all on the shoulders of excellent and highly motivated and hardworking students and postdocs and assistants and whatnot. And what I showed you really doesn't do justice to their work. It's just a small taste of it. And I really thank them all, and hope that most students will come and continue this work for the next 20 years. So I thank you for your attention, and I bring it back to Shimon. If is time for any questions, I will be happy to answer.
Yes. Hello. Yeah. Thank you very much, Dan Yakir. I'm applauding this great talk, and we have several questions. We have several hundreds of people who are listening to you. I'll first ask you just something that interests me. So what enables the arid areas to be carbon storing efficient? And if there's something that enables it, how can we use it for geoengineering, as you mentioned? Dan? He's out. 1 minute. Sorry, 1 minute. Okay, Dan?
Hello. הוא עדיין משתף מסך? דן?
כן.
אני חושבת.
One minute. So if you have questions, so please feel free to ask them.
Can you hear me now?
Yes, we can hear you and see you. Yes.
Okay.
So So you heard my question, or?
No, please repeat.
So I will repeat my question, and then I'll ask several questions from the audience. So the question is, what enables the arid areas to be carbon storing efficient? And if there's something that enables it, how can we use it for geoengineering?
Well, I think I tried to show why is it carbon use efficient, because it was able to adjust the seasonality to the early spring and mobilize all these other methods to keep a relatively high GPP, and on the other hand, limit the water loss during the rest of the season. So if you maintain relatively high carbon uptake and you are able to limit water loss, the translation of this ratio is high water use efficiency, and that's the success of the forest. Now, in terms of geoengineering, I mean, Yakir itself is an example of geoengineering. This is a plantation. This is a forest that was planted, in fact, beyond the limit of the normal forestation. Normally, it's assumed that you don't plant forest beyond 500 millimeters of rainfall. Yakir is planted in an area that has only 290 millimeters annually. So in a sense, even though they didn't consult us, the people who planted the forest, they actually did intuitively a sort of a geoengineering. They pushed the limit of forestation. They planted the forest that is absorbing 1.5 tons of carbon per hectare every year. My point was that this is just a model system. If this can be done in Yakir, it can be done in many other places. And the land, the dryland has a good potential because there are many areas that are open and available for forestation. Of course, you have to balance it with other activity, protection of nature, biodiversity, and so on. But I think there is enough room for everything.
Okay, so I have another question out there. So for the positive effect of plantations and precipitation on plantation, would this be mainly recycled ET or moisture drawn in from outside of the domain?
Yeah, that's a good question, because in many places the vegetation is mostly recycling water. In the Amazon, for example, 50% of the rain is recycling. But in the experiment that Gil Yosef has done, he actually was drawing moisture from the ocean, both in the Sahel and in Australia. The vegetation actually changed the patterns of atmospheric circulation, and these changes that we don't have time to go into details, but it removes some of the obstacle of moisture movement from the ocean into land, and that allowed increased precipitation. And of course, the vegetation then recycles some of it.
Yeah. So I have three more questions at least. So for the NPP, GPP graphs, is there a gradient in response if we compare ecosystem activity from Finland to Greece to Israel? This is from Lina Ababane.
Yes, so it's true that I showed in the slide only the normalized GPP, so everything was 1, but there are large differences in the absolute values, and the GPP in Israel is in Yakir is of course in absolute numbers is much lower than in Finland or even in Greece for that sense, by tenths of a percent. But I was trying to say that this relatively low GPP is still very efficient because respiration is also depressed by the dry conditions and the low quality of the litter, such that the ratio of NEP to GPP is high, and this ratio.
I have 2 more questions at least. So from Pradeep Day from India, as carbon saturation potential for the arid zone is low, is it possible to develop an organic application rate vis-a-vis aridity index?
Yeah, actually, Rafat Kubacha that I mentioned that did the carbon turnover study in Yakir, he also estimated the carbon saturation, and in fact, in our case, in these calcareous soils that we have around here, the carbon saturation is much higher than the current carbon content in the soil. So at least in the soils that we examine, there is still a potential without manipulation as the person is suggested. This can come up maybe later, but at the moment, there's still a lot of potential to increase the soil carbon content in natural way.
So just I think we'll give the last question from Stan Szymanski that I think is related to the previous question. He's asking, what is the carbon storage capacity of Yakir and similar places? I mean the maximum storage, not the sink strength.
So yeah, so this is related to the previous questions, and we think that I actually don't remember the exact number, but I think that Rafat's estimate of the carbon saturation, the fraction of the saturation in Yakir is something in the order of 30%. So it's far from saturation. So in terms of storing carbon in the soil, the potential, at least in our case, is still large. Carbon storage above ground is much more limited, also because the turnover is fast, because the density of the forest is very limited. The carrying capacity based on the precipitation and other factor is limited. So, but below ground is still a potential. We can probably triple the amount of carbon that is now stored in the system.
So just last question from Miriam Waltz. Is root growth or tree canopy more effective for maximum carbon sequestration?
I don't know the exact answer, so I have to partly speculate. But as I said, we think that the potential is below ground. Of course, in our region, the soil level is very limited. It's a very shallow soil above
or stop or mute the screen before going to the Zoom. Okay. Thank you very much. Thank you.
Thank you.
Bye-bye.
Bye-bye.